I'm Paul Glenn. I'm the president of Bauer Associates. We've been in the optics metrology business for about 30 years now. And what we do is build instruments that are just different from others. This is one of our favorite achievements. This is the 4-point stitching profilometer, 4 PSP. It uses 4 probes, 4 laser beams. If you look under this platter, you'll see the red laser beam. There are 3 more. What we do is rotate those 4 laser beams with this platter around a circle on an optic. That turns out to give us enough information to get a nanometer level profile of the surface along that circle. We then use this huge hexapod to position the platter over many positions on the optic, and just like a spirograph, you get all these circular traces, and we put all those together in some more math, and we get a profile of the surface shape. What we needed to make this work was not only a very accurate, smooth rotary motion, but this giant hexapod to be able to move to all the different places around a large optic. And so we have actually mapped this hexapod in its entire work volume down to the few micron level. We have 2 different frames. We have a frame in here that carries the rotating frame of the laser and the probes and this platter with a very high strength but very stable flexure approach. We kinematically attach this inner frame to an outer frame. So it's really 2 hexapods, 2 entirely different hexapods, the encoding hexapod and the actuation hexapod. We actuate the outer frame with these 6 electric pistons, and we encode with 6 encoders. So we, through a lot of math, calculate where we want these encoders to go, given where we want the instrument to go on the mirror, and then we just have the PMAC feed these motors and enclose its own servo loop motor by motor. And that's been a nice thing about using the delta tau PMAC, is that we can make these 6-dimensional trajectories with positions and velocities and times, and we can follow them just beautifully. This entire structure down here, which holds the 4 probes, it's carried by this steel structure. But you think about the accuracies that we're trying to get to. We're trying to get to accuracies of 1 nanometer. So the whole secret of this is that the 4 probes are stable with respect to each other. And it turns out, by proper choice of where these 4 probes are, that's sufficient to get a nanometer level measurement. But we built this enclosure for the instrument, and it's thick insulation, nice clean room quality plastic on the inside. But most importantly, it does 2 things for us for the optic. With the insulation, the temperature changes are slow, and just the walls themselves cut out the wind. Turbulence-wise, it's a very quiet environment, and thermally a very stable environment. This whole assembly will cruise sometimes as little as just a few millimeters above the optical surface. And so we want that trajectory to be very smooth and coordinated. So the capability that we've used for that is to calculate a trajectory in all 6 dimensions across the optic, feed it into the delta tau as a position, velocity, time trajectory, and it's just absolutely smooth at how it flies over the optic and goes to the next position to measure a hoop. We've done all kinds of things, and what ties them all together is that they all require some kind of coordinated motion to be accurate, predictable, controllable. The delta tau stuff has always been a very good way for us to achieve that.